Hey class, we're going to move on to the next page in 3.2. So this is page 51, and we're going to do some more examples of multiplication rule with conditional probability. Here's an example where we know the probability of a specific event, 85%, and the knee surgery is going to be performed on 3 different people. So when I read that, it's looking like an independent example, right? So we have independent events, which means we can just multiply probabilities together, and we are good. So all 3 successful, that's just the probability of success, success, success. Let's just write it like that. And all I got to do is find the probability of the first success, multiply it by the probability of the second success, times the probability of the third success. So that's how I'd write it out with the notation. And we know that each success is 85%. Make sure to convert that to a decimal when you're doing calculations. So I'm going to write that as 0.85. And then the second one is also 0.85. And the third surgery is 0.85. Right? Or you could write that as 0.85 to the third power. Right? If you want to do that calculation easier in your calculator. And so this is about 0.0614. Now how about the second one? None of the 3 are successful. So if it's 85% successful, then 15% would be the opposite of that, right? Because they have to add up to 100%. So 15% not successful, right? So let's go with probability of, let's call it fail. Fail, fail, fail. Right? And then I'm going to skip just multiplying that out. I just know to multiply them all together. So it's going to be 0.15 times 0.15 times 0.15, or 0.15 to the third power, which is approximately 0.003. Yeah, that seems to make sense. It would be pretty rare with a high success rate that you would get 3 fails. Now this third one, at least 1 success. Okay, here's that at least 1 again. At least 1, the best way to accomplish that, so when you see probability of at least 1 success, the best way is to find the opposite of that. And the opposite of at least 1 success is that they all fail. So this is going to be the same as 1 minus the probability of all F, or FFF. Right? Because at least 1 success, that will be either 1 success or 2 successes or 3 successes. And the only scenario that doesn't fit that is just all fails. So if I find the probability of all fails, I know I've found the opposite of the answer, and then I can subtract from 1 to get the answer. So this is going to be 1 minus, and I already found that in the part B. Right? So this is going to be 0.997. And there you go. Okay. And then would it be unusual then for all 3 knee surgeries to be unsuccessful? Yeah, I mean that was part B, 0.003, so that seems very unusual. Our marker though is going to be for now 0.05, so anything less than 5% we're going to call unusual. Okay, and that's on this little note right here. Okay, moving along, we have these problems with these tables again. So two-way table, and there's all sorts of questions that can be asked with these two-way tables. So let's start with what's the probability of a nursing major? So how many nursing majors do we have? Looks like right there, there's the total number of nursing majors, and there's the grand total. So I'm going to use those numbers and divide them. 795 nursing majors out of 3,537 total. If I calculate that out as a decimal, we get 0.225. How about the probability of female? Female, let's see how many total females, boom. Total, boom. So those are the 2 numbers I'm going to use. Okay, so those are the straightforward ones, just kind of warming us up. Okay. The next one is a given that. So we've seen those already, those given that problems. Right. When you see given that, then you're going to look at that part, given that the student is female So let's find the total female, 24, 27. That automatically is your bottom number. Right. Now, stay within that row, right? And then look at the first part, nursing major. That's the 700. So the top number is 700. And that's it. And then convert to a decimal. And you're good. Okay. The next one is kind of a new one, right? Because this one we have an and. So the way I accomplish those, if it's an and problem, first off, the bottom number is always your grand total. Right? So even though it's an and, I kind of feel like, oh, I got to multiply something. If you're given a table, you don't have to do the multiplication. You just got to find the right numbers. So the bottom number is always the grand total for and problems. And then now just look at your table and which number is both nursing major and female. So that should lead you to that 700, right? They're in both the nursing major column and the female row. So that's the top number. And calculate that out, 0.198. Okay. The two that are most commonly mixed up are C and D. Right, they kind of feel like they're the same, nursing major given that the student is female, and nursing major and female. But they are slightly different. You notice I calculated them in different ways. So if you follow the way I did it, you should be good on those. Finally, are the events being a female student and being a nursing major independent or dependent? So let me direct you to A and C. Right? A is the probability of a nursing major. It's 22%. But if I put a condition on the probability, the condition being in part C, the student is a female, notice how the probability jumps up to 29%. So because A and C are different, the condition of being a female does affect the probability of being a nursing major, and therefore they are dependent. So basically, if I write an answer here, I would say since A and C, as I explained it, are different, and I would probably say significantly different, and then later on we will get into that, like, okay, what if it's 22 and 25%? Is that far enough apart? That's a little subjective at this point. We would have to say dependent on that one. Okay, so hopefully that made some sense. Okay, one more page for 3.2. Here's another one where it's a conditional probability. Research shows that approximately 1 woman in 700 carries a mutation. And then about 71% of women with this mutation develop skin cancer. So find the probability that a randomly selected woman will carry the mutation in the gene and develop skin cancer. And I have those probabilities, so the first probability is 1 out of 700. And then given that they have the gene, 71% of the women develop skin cancer. So I would just multiply this by the 0.71. That 0.71 has the condition already baked into it, the way it's read. Right. So that's all I got to do with this one. Notice I converted that percentage to a decimal for the calculation. Right. So basically I'm going to do 0.71 divided by 700. This ends up being about 0.001. So maybe double check that with your calculator. Okay, here's another problem. De'Aaron Fox makes free throws 78% of the time. If he shoots 5, what's the probability that he makes all 5? So here we have independent events, right? Because we would have to assume that each attempt is independent of the other. I guess there might be a little bit of streaks involved. Maybe you miss one that psychs you out for the next one. Okay, I can kind of see that, but can't really assume that, so we're just going to assume independent events. So that means the probability is 0.78 times itself 5 times, or just 0.78 to the 5th. And so that would be a 0.289. Okay. And then finally, a student takes a true or false quiz. They randomly guess the answer to each question. What's the probability that they get at least one right? Okay, so remember our little formula, probability of at least one correct would equal 1 minus the probability of none correct, or all incorrect. Okay, so this is the case where we're going to find the opposite. We're going to find the probability of getting none of them right. And none of them right, the probability that you get a single question wrong is 50%, because it's true or false quiz, right? Got a 50-50 chance. So 50%, 0.5. And then you're doing 6 questions. That would be to the 6th power. And we have it. So then we're going to do 0.0. This is 0.15625. Okay, that piece right there, that's the probability that you get all 6 wrong. Right. And remember, the opposite of all 6 wrong is at least 1 right, and that's what we want. So to get the opposite, we subtract from 1. Okay, and then that calculation is 0.984. Woo! High probability of getting at least 1 right. So if all you need is 1 correct answer, you can just guess. Okay, I think that's the end of our 3.2. Hope you've enjoyed it, and I'll see you for 3.3. Talk to you later.